Good evening, students. As you people knew that we are discussing the stack architecture. For those people who joined freshly for this week, this is Anil Prasad taking computer architecture for you guys who are GATE aspirants for GATE 2021. Okay, so getting into the topic, now we are discussing the architecture of a stack. In fact, we are designing a CPU. In the CPU, we are designing the register set. The register set can be designed in three ways. The first one is single accumulator organization. The second one is general register organization. And the third one is stack organization. When it comes to the stack architecture and organization, the stack can be organized in two ways. The first one is the register stack and the second one is a memory stack. So let us have a small recap about the register stack. So now when it comes to the register stack, you know that the register stack will be available within the processor. Okay, so for an example, if I can draw the register stack this way. If I can draw the register stack, with a size of 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. Right from 000 to 111. Okay, initially stack pointer points the 000 element in which there is nothing, because whenever the stack is empty, the stack pointer is initially going to show the 000 in which there is no element. Whenever we want to push an element, initially stack pointer will get incremented, then the element will be pushed. Okay, so in that case, once the stack pointer is pushed, when the stack pointer is incremented, stack pointer comes to 001 in which the element will be available. The moment stack pointer reaches to 111, final element will be here. Let us say E7. Still this place is left. I told you how to use this space, because when SP is equal to 111 and when we want to push one more element, then 111 will get incremented. So 111 plus 1 is equal to obviously 000, because the end carry 1 will get discarded since the stack pointer is simply equal to just 3 digits. This logic has been explained in the previous week. This is all about the register stack which is implemented within the processor. Now there is something also called as a memory stack. Now let us have a look at the memory stack, how it is going to get designed. You know that we do have a main memory, right? We do have a main memory. Let me draw some memory here. Let us consider that this is memory. Fine. Okay. I will draw the main memory. Otherwise, I'll use the PPT sheet. Yeah. Here, let us see that This is the memory stack. If you can have a look at, this is the main memory in which there has been a stack. Okay, so first of all, you need to understand why do we require a memory stack? Why do we, need to design one more stack in the main memory? This is purely because every process what is being executed will require a specific and own stack. That means that whenever you write a program, that program will have its own and a specific stack. If you do have 100 programs in the main memory, each and every program will use its own stack. The stack space cannot be used by any other program, which means that every program will have its own stack. For that reason, we need to also understand the logic of the memory stack. Okay, now let us understand how the memory stack is going to be designed. If you can stay focused, I am going to explain you something which is really important to understand the stack here, because so far till now you've been familiar with the stack in some way, in only one direction. I am going to show you now another dimension of the stack which is going to open the complete design logic of the stack. Stay focused and understand. Yeah, now let us say that I am going to design a memory stack. Okay, here itself I'll design because wait. Let us understand this is main memory. Okay, this is my main memory. Okay, now you know that the memory will be starting from 0. There will be some specific size of the main memory. As you know that we started with a memory with a capacity of 4096. The people who are following my lecture carefully, they do know that we designed a main memory unit with a size of 4096 words. Okay, let me take the same example to explain you guys about the memory stack. I do have a main memory which is equal to a size of 4096 words. Okay, so that means that I do have addresses right from 0 to 4095, right? 4095. I do have a total of 4096 location in which the addresses are from 0 to 4095. Okay, now let us understand a few things before you design a memory stack. The first question before you design a memory stack is where to design. See, you do have, let me make it very clear. You do have a total of 0 to 4095. Several locations in the main memory are available. Let us say that being a designer, you want to design an 8-element stack. Okay, you want to design an 8-element stack. The question is where this 8-element stack will be designed. Rather, what is the space that you are going to get from the main memory? Let me tell you something very clearly that if you want to design a stack, you can't use the space from the 0th location. Okay, write it somewhere or remember or digest whatever. That is memory 0, right from memory 0 till a few locations. Any main memory, try to understand very clearly. Okay, in this main memory, this is a 0th location, first location, second location, third location, so on. Okay, being a designer, you need to understand that usage of the initial locations of the main memory will be prohibited. Being a designer, once again, you need to understand that you can't design anything In the initial locations of the main memory, initial locations of the main memory will be system reserved. Will be system reserved. Sir, what is this system reserved? Why we can't use this? You are going to understand very clearly. Being a designer, let me tell you that I am going to take you people to every possible direction of the computer architecture design. Initially, just for now, you just remember that if you want to design something, it is not possible to design that in the initial locations of the main memory because it is system reserved. And these locations will be used for what we are going to understand later in the lateral classes. So being a designer, you knew that you can't design your stack in these locations. Okay, so which is the best location to design a stack? If you want to design a memory stack, let me tell you, let me write it here. If you want to design a memory stack, it is always better to design it from final sections of the memory. Sir, what is this final section? There is nothing. You cannot use the initial section. The initial section is system reserved for what we are going to understand later. So what you do is you go to the last locations to design your stack. That's it. Okay. Now I am going to design my stack right from 4095th location. So I am going to design a stack from 4095, 4094. This is 93, this is 92, this is 91, this is 90, this is 89, let us say this is 88. Okay, now I am going to design my 8 element stack right from 4095 to 4088. This is 4088, this is 4095. The stack is designed right from 4095 to 4088. Now you know that the stack pointer initially is going to point to the base of the stack. As the stack is empty, as you can clearly see, the stack is currently empty. When the stack is empty, the current stack pointer will be the address of the initial location of the stack. What is the initial location? The initial location is 4095. As it is 4095, Lokesh Parab, I had doubt related set associative mapping in two-way set associative line of cache gets reduced to half. So we can say that the cache memory will get reduced by 1 bit. Lokesh Parab, now we are not discussing about memory. I am going to explain you about memory. When I get into memory, now we are not discussing anything about the main memory. Okay, memory is altogether a different concept. Okay, now initially we started with the processor design, right? When we started with the processor design, let us complete the design of the processor. In the processor, we are designing the register set. The register set is of three kinds: single accumulator, general list, and stack organization. Stack will have to be designed in both processor as well as the main memory. That is the reason why we are discussing something about the main memory. Other than that, we are not discussing about the main memory because the current topic is not main memory. When it comes to main memory, when we go to main memory, you are going to completely understand the mapping techniques. Cache main memory to the cache memory mapping techniques. Address mapping, direct mapping, set associative mapping, and associative mapping. I am going to explain. But meanwhile, hold on. Just be in the concept what is being discussed concurrently right now. After which we are going to go ahead with the rest of the topics of the computer architecture. Let me ensure you once again very clearly that all the topics will be completely covered. Okay, before you go to attempt gate. Now we are discussing about the stack. Let us confine our discussion to the roots of the stack. That's it. Within the framework of the stack. Now we are discussing about the memory. In the main memory, I do have stack is designed. The stack is the origin of the stack is 4095 and the top of the stack is 4088. Okay, now the stack pointer, as you know that it is going to show initially the base element of the stack. The base element of the stack's address is 4095. In 4095 there is nothing, right? Yes or no? Now let us understand that we are going to perform a push operation. Stay focused. I am going to tell you something which is very different from what you already knew about the stack. Once again, let us stay focused. Memory stack is originated right from 4095 to 4088. The initial location of the stack is 4095. Final location of the stack is 4088. Stack pointer is showing 4095 because there is no element in the stack. Okay. Now imagine what is going to happen during a push operation. You know that the stack pointer will get updated to the next location. In this updated location, element will get pushed, right? Lokesh Parab, answer me. Whenever we perform a push operation, what was happening? Initially, stack pointer will have to get updated to the next location. In the updated address, element will get pushed, right? Answer me. I am waiting. You can't push in 4095. You can push only in the location which is updated from the current SP. Yes or no? As you can clearly see here, if you want to update stack pointer will get decremented. You got me? This is the very point that you need to understand. So far, what you learned every time when you talk about the stack and when you talk about a push operation, you by-hearted that during a push operation, stack pointer will get incremented, after which element will get pushed. This is the what you call thumb rule, what you have already digested, right? Now, I am going to take exactly that point. Being a designer, you need to understand that there is no restriction for a designer to go in a specific way. You need not go in a specific way. You can clearly see here. Now, my stack has been designed from 4095 to 4088. Initial value of the stack pointer, the base of the stack pointer is 4095, top of the stack is 4088. Initially, stack pointer is showing 4095. Now, when you push it, what will happen? Stack pointer will get decremented. So, during a push operation, stack pointer can also be decremented. It depends on the design of the stack. Okay, if the stack is designed in this way, then stack pointer will get decremented during a push operation and incremented during a pop operation. Did I make it myself clear? Okay. Now, in this regard, let me explain you. Being a designer, what are the design logics that are available for a designer to design a stack? Okay. There are two ways you can design the stack when it comes to push and pop. One is upward stack. Second one is downward stack. What is the upward stack? If the designer designs a regular stack, which grows in the upward direction. This is the upward stack. Otherwise, if the designer decides to go in a different direction, that is what you have watched just a short while, that is from 111 to 000. Did I make myself clear? That is, if the designer uses this convention, initially he can place the stack pointer at 111. Okay, finally stack pointer reaches to 000. Did I make it myself clear? At that time, stack point during a push operation, stack pointer will get decremented. Okay, here in the upward stack, SP is equal to SP plus 1, but in a downward stack, SP is equal to SP minus 1. Now let me tell you, okay, apart from 8086, all the advanced computer architectures uses the convention of downward stack only. Okay, right from 32-bit architecture. I don't need to explain what is a 32-bit architecture. Do I? Because 32-bit architecture meaning one register size is equal to 32 bits. I explained you clearly in my first class. So, other than 16-bit architecture, any other architecture uses the mechanism of a downward stack. Okay, so the stack pointer will get decremented during a push operation and gets incremented during a pop operation. This is all about the memory stack. So once again, just a small recap of a memory stack. The memory stack will be available within the main memory because there is a need of having a stack for every program. Every program requires its own and dedicated stack. For that reason, we should also understand the logic of the memory stack, how it is designed. Generally, apart from 8086, all the other designers would like to go for a convention of a downward stack, which is during a push operation, stack pointer will get decremented, and during a pop operation, stack pointer will get incremented. Okay, so this is how the memory stack is going to be designed. And one more small difference between register stack and a memory stack. Let me tell you. This is also important to understand. Let me draw the register stack what we have designed yesterday, rather yesterday week. 8-element register stack. Right? Now here, initially stack pointer is equal to 000. When you push an element, stack pointer will get incremented because the convention what we have used in designing a register stack was an upward stack. So in the upward stack, stack pointer grows this direction, that is incrementing the stack pointer during the push operation. So let us ignore that. The moment you reach the stack pointer to 111, still this element is empty. So SP will get incremented for one more time, that is 111 plus 1 is equal to 000, right? So that SP will come back here, and here in this location the final element E8 will get pushed. That is what we understood in the last week. Now let us understand here. In the memory stack, it is not possible. That is, let us say initially the stack pointer is equal to 4095. That is, there is no element, right? Now when you want to push an element, you know that the stack pointer will get decremented. Did you get it? So it goes to 94. The first element will get placed here. Second element will get placed here. Third element will get placed here. Fourth element will get placed here. Fifth element will get placed here. Sixth element will get placed here. Seventh element will get placed here. Here the problem is, if you decrement it for one more time, you can't come back to 4095. There If you update the stack pointer, you will anyhow come back to 000 because 111 plus 1 is equal to 000, 000 minus 1 is equal to 111, right? So we do not move anywhere other than, we do not go anywhere from the boundaries of the stack. Every operation will get confined within the boundaries of the stack only, right? But in the memory stack, this cannot be guaranteed because if you further decrement 4088, you will go to 4087, right? Sanket Sahasrabuddhe, hello. Yeah, hello. You joined late, but anyhow, you just stay focused. I'm explaining one important concept here. Yeah, fine. When it comes to, 4088, if you want to decrement further, where it will go? It will go to 4088. Sorry, 4087. Let me show it here. Initially, stack pointer is equal to 4095. Stack organization. Initially, stack pointer is equal to 4095. Right? Now, there is no element. There is no element. Now, if you want to push an element, what you need to do? You need to decrement a stack pointer. When you decrement a stack pointer, it goes to 4094. When it goes to 4094, then you are going to push the first element even. So stack pointer will be here. Stack pointer is equal to 4094 and element 1 is pushed. If you want to push one more element, decrement the stack pointer to 4093. Here, element 2 will get pushed. Element 3 will get pushed. Element 4 will get pushed. Element 5 will get pushed. Element 6 will get pushed. And element 7 will get pushed at 4088. But still we do have one more empty location, that is 4095. In the register stack, you know that 111 plus 1 takes us to 000. But in the memory stack, there is, it is not possible because 4088 minus 1 will be equal to, let us, 4088 minus 1 is equal to 4087, right? This 4087 is out of the boundary of the stack, right? So 4087 is here. Okay, this is purely because the stack pointer size is equal to the address length of the main memory. Okay, so but in the initial stack, in the register stack, stack pointer size is equal to just 3 digits. I will write it here. In the register stack, stack pointer size will be equal to 3 digits because there is no restriction. In the register stack, we have used an 8 element stack. So the stack pointer register must be equal to 3 digits. That was in our hands. But when you go to the main memory, you need to obey the rules of the main memory. In a memory, address is equal to 12 digits. Yes or no? Lokesh Bharat, my question is to you. What is the address length of the main memory? Address length of the main memory is equal to 12 digits, right? Yeah. In main memory, our main memory is of a size is equal to 4095, which means that I require 12 address bits because 2 power 12 is equal to 4095. So the address register size must be equal to 12 digits. Any address will be equal to 12 digits. What is stack pointer? Stack pointer shows the top address of the stack in which there is an element present. Okay, so here the problem is we cannot get confined within the boundaries of the stack in the main memory. So here in this case what we do is we will write an if condition. Okay, every time when the stack pointer goes out of the stack, we will use an if condition. Being a programmer, we know how to write an if condition. If stack pointer is equal to 4087, then stack pointer is equal to 4095. In that way, we can keep our stack pointer within the limits of the stack. Okay. It was not needed in the register stack because 111 plus 1 is equal to 000. 111 plus 1 is equal to 000. So the stack pointer will be moving front and forth in between 000 to 111, again 111 to 000. That's it. So this is the difference between a register stack and a memory stack. Did I make it myself clear, Lokesh? Any doubts, you ask me right now so that I'll be able to clarify this. Because I'm going to explain you a gate question before we finish today. Are you still there, Lokesh? Yeah, good. You got it right. Very good. Okay. Now, this is the difference. The main key points that are needed to be recapped here is a register stack is embedded to a processor. Okay. Second one is memory stack is designed in memory. Okay. Now, let me give you some complete idea, the complete idea about how the stack is going to be used. Okay. So here, once again, this is my memory. This is my processor. In the processor, there is a stack. Okay. There is a stack. There are registers. Sanket Sahasrabuddhe, sir, what are different classes of CPU registers? Logesh, sir, can you explain what is a register computing? What do you mean by register computing? Wait. I'll come to your question. I'll answer your question just before we finish. Okay, fine. Sanket Sahasrabuddhe, your question is, sir, what are different classes of CPU registers? There are two classes of CPU registers. One is special purpose registers, one more is general purpose registers. That was explained in my initial class. Okay, but anyhow, you just write it somewhere that special purpose registers are going to store only a specific data, but general purpose registers can store anything. Once again, there are two classes of registers. One is special purpose registers and one more is general purpose registers. What is the difference? When it comes to general purpose registers can store any data. But when it comes to special purpose registers are designed only to store a specific data. For example, program counter. Program counter only will store address of next instruction. Okay. But when it comes to a general purpose register, R1 can store anything. It could be an address or a data or an operand or anything. Okay. A general purpose register can store anything. Okay. Sir, fine. Sairam is asking the question. I think he's asking about the difference between general purpose registers and special purpose registers. Is it, Sairam? Fine. If that is the question, there are two classes. One is special purpose registers. And second one is general purpose register. Okay, what is a special purpose registers? For an example, I'll give you example. There is something called a program counter. There is something called an instruction register. Program counter stores address part of the next instruction. I will write it as next instructions address. Next instructions address. Okay. Program counter always stores next instructions address. And there is something called an instruction register. Instruction register stores the current instruction that is getting executed. Okay. Current instruction that is getting executed. Okay, for an example, in the main memory, stay focused and understand carefully. This is already explained in my previous class, one of the previous classes. If people did not attend, anyhow I'm explaining. See, let us say CPU is executing 20-second instruction. This is my main memory. Currently CPU is executing 20-second instruction. Okay, so this is the current instruction. I will write it as CI, which means that the current instruction. If 20-second instruction is the current instruction, what is the next instruction? Next instruction's address is 23. Did I make it myself clear? So if the current instruction is 22, next instruction 23. So program counter always points to the address part of the next instruction. Okay, so here in this case, in our case, program counter value is equal to 23. Okay, if the current instruction is equal to 23, program counter value is equal to 24. Okay, now what is the instruction register? Instruction register is going to hold the current instruction. In the 20-second address, there is the current instruction. Okay, this instruction will be made available in the instruction register. Okay, Lokesh, wait for some time. We do have a few questions from these people, after which let us go back to the start again. So let us understand that these are special purpose registers. For an example, program counter. Program counter is the next instructions address. Instruction register holds the current instruction, right? So special purpose registers are designed to hold only some specific data. Program counter cannot hold any other thing than next instruction address. Instruction register cannot hold any other thing than current instruction. Okay, and there is another category of the registers, another class of the registers which are called general purpose registers. These general purpose registers labeled generally such as R1, R2, R3, so on. Okay, Rn. What are needed to be stored here? What are the things that are needed to be stored? Don't worry, there is no restriction on the things that are stored in the registers. Okay, these registers can hold anything. For an example, R1 can hold an operand or an address or anything. Generally, registers holds the operands of the program. For an example, you declare a variable. Okay, A is equal to 50. You know that A is a memory location. For an example, for A, processor decides to give 450th location. In 450th location, the value of A will be present, right? So whenever you use this variable in a program, let us say that this variable is being executed. At the time of execution, this variable will get transferred to one of the general purpose registers. Okay, so whenever you use A, it is declaration. A is equal to 50, it's just a declaration. Now when you try to execute the program, A will get used. For example, A is equal to A plus 1. In order to perform this, what is needed to be done? This A value will get transferred to a processor's register. For an example, in this case, the processor decides to allot register 2 for this A. So R2 is equal to 50 right now. But generally what is R2? R2 is a general purpose registers. But in this case R2 is given for A. A value will be transferred to R2. Then R2 value will get incremented because this is a processor register. After which R2 will be equal to 51 after the incrementing. Then the value of 51 will get transferred back to the memory location A. Did I make it myself clear? Okay. So this is how it is going to be done. The register stack is embedded to the processor. Okay. Now, yeah, Sanket's control word means I will discuss about a control word. Maybe not in this class because see the control word meaning we need to design the control unit. Mr. Sanket or Saket, he is Sanket. Okay, let us understand. We are designing, in fact, right from the very first week, we are going in a flow. We started designing a processor. Okay, if you want to design a processor, you need to design three things. One is a register set. Second one is control unit. And the third one is ALU. Now we are in the process of designing a register set. When we design control unit, you will be able to understand what is the control word. Okay. The design of the control unit will take maybe a week. Okay. Next week also we confine ourselves to the discussion of the register set. After which, after the next week, I am going to explain you guys completely what is control unit. Then you are going to understand about a control word. Okay. Now in this case it is too early to discuss about a control word. Okay. So you just hold on for a while. But anyhow, as you asked me, let me explain. The control unit is going to send the control signals to each and every register and a memory location. For an example, in a specific clock pulse, let us say there is a clock pulse T2, meaning this is the second clock pulse in the instruction execution. In the second clock pulse, the control unit will have to make a transfer from memory of the address register to instruction register. Let us understand, you are not going to get anything because we did not come to this part, but I am going to explain you superficially what is a control word. Memory of the address register, the value of the memory of the address register will get transferred to instruction register, and in the same second clock pulse it is going to increment program counter. PC is equal to PC plus 1. Now control word is all the control signals that are sent to memory of the address register and the instruction register and the program counter, because if all these operations are needed to be performed, then these locations must get selected. Control unit, let us understand clearly. Mr. Sanket, stay focused here. There are several things in the processor, right? There are several registers, R1, R2, R3, program counter, address register, instruction register, main memory, locations right from 0 to 4095. There are plenty of locations in the computer system, right? The control unit job is to initiate the operations in between the locations that are required to be participating in a specific clock pulse. For an example, there is a second clock pulse, that is T2. In this T2, only there has to be a transfer in between memory of the address register to the instruction register, and the program counter should be incremented. Apart from these elements, apart from these locations, no other location of the processor should be invoked. So instruction register will get a control signal, address register will get a control signal, program counter will get another control signal, all these control signals that are sent to the respective registers and memory locations in a specific clock pulse are going to form a control word, because this control word is going to be initiated, rather is going to initiate only those elements, rather only those locations which are required to be invoked in any specific clock pulse. Okay, that is what a control word is all about. Once again, what's a control word? Control word means all those control signals that are sent to the respective locations in a specific clock pulse. For an example, in the T2, there is a register accumulator. Accumulator should not be selected in T2 because accumulator presence is not there in T2. Okay, which are the locations and the main memory location and the main memory are participating here? Instruction register, address register, program counter. Only these three locations must be invoked. Rest of all the other location in the processor and the main memory should be kept quiet, because those are not participating any transfer in T2. And when it comes to T3, what is T3? Another clock pulse. In that respective clock pulse, there will be some more elements and the locations will get invoked. Okay, so what is a control word? In a nutshell, simply speaking, control word is nothing but all the control signals that are sent to all those locations which are needed to be invoked in any specific clock pulse. That's it. Okay. Sir, good book for the computer organization and architecture to be used. Write it down somewhere. Maurice Mano, Computer System Architecture. Okay. Computer System Architecture. Write it down somewhere. I think in the market right now, edition 4 is available. Buy it. Okay. And I think there's also an online copy. If it is available, just download it. It has to be your handbook. That must be your holy Bible for the computer architecture. Okay. But the thing that is available in the computer system architecture in an abstract form, I suggest you reading that, because if you can understand that book, you are going to understand the complete design logic and semantics of the computer system architecture. Okay. Anyhow, the suggested book is Computer System Architecture. That must be your handbook and a holy Bible for the computer architecture. Okay, fine. That is it. Let's come back to the stack again. I think we are running out of the time, but anyhow, we will finish as much as we can for this week. If it is, still something left, we will discuss in the next week. Now we are discussing about the memory stack. Okay. So, what are we discussing? Register stack in the processor, memory stack in the main memory. Yeah. Now, this is a processor. Let us come back, Mr. Where is this guy? Lokesh. Mr. Lokesh, and let us come back to the stack. This is a processor. Okay. And this is main memory. All of you stay focused. Even though you were not present in the previous class, doesn't matter. I'm going to take necessary steps in such a way that you're going to understand everything. I'm going to explain in such a way that you're going to understand everything what I'm going to explain. Okay. Now here, understand this is a processor. In this processor, there are registers, R1, R2, program counter, something. These are the registers. But this is a stack. Okay. This is a stack. This is the main memory. I do have several programs in the main memory. Several programs in the main memory. Okay. So let us say that this is program 1, program 2, program 3, program 4, program N. Okay. As I already told you people that each and every program will have its own stack. Yes or no? All of you answer me. Did you Understand in C? Did you hear this? Have you ever heard that every program that has been written will have its specific and dedicated stack? You know that? I want answers. Do you know that each and every process or a program will have its own and respective stack and dedicated stack? I want answers right now. Anyhow, fine. Okay. This is a processor 1. This is a process 1, process 2, process 3, process 4, process N. You need to understand that every process will have its own stack. There will be some specific values will be pushed into the stack. Okay. This is P1. This is Pn. Every process, okay, if it is for the first time, fine. Doesn't matter. Again, write it down somewhere. Every program which is in the main memory requires its own and dedicated stack. That's it. If there are 1000 programs in the main memory, there must be 1000 different stacks. Okay, because each stack is going to service one program. Okay, there are some specific things that are needed to be pushed into the stack. Every program will need to push a specific things. What are those things? Don't ask me right now. I am going to tell you shortly. Okay, for now, there are 1000 programs. 1000 program meaning each and every program requires its own stack. That means that main memory has 1000 different stacks. Each program a specific stack. Fine. You need to get it digested. Okay, that is the reason why I am explaining you for these many times. Now you are no more a programmer, sir. You are no more an end user, sir. Now you are a designer. You are a designer of the system. You need to understand the design logics and semantics of the system. Fine. Okay. I do have several stacks. Each stack for a specific program. But when it comes to the CPU, CPU has only one stack. Okay. Sanket Sahasrabuddhi, sir, voice is not clear. Fine. I will stay more close to my mic. Is it clear right now? Fine. Okay. Now, let us take that this processor is executing program 3. Okay. So, what do you mean by this? When processor executes program 3, all the program 3's values, you know, the variables and the constants and whatever will get transferred to the registers. Program 3's elements will get transferred to the registers. Okay, and program 3's stack is program 3, right? Program 3's stack values will be transferred to the register stack. Once again, the processor is going to have, of course, processor has a few registers and a stack, and these registers are going to hold the values of the currently executing program. When program 3 is executing, all the values of program 3 will get transferred to the local registers of the CPU. And processor 3 also has a stack, right? These stack values will be transferred to the register stack. Now process 3 gets executed. Program 3 gets executed. Finished. Program 3 is over. When program 3 gets over, all the registers values will be cleared. And then, in addition to stack, okay, along with the stack, all the registers values will be cleared because process 3 or program 3 is completely executed. There is no point in holding the program 3 values within the processor anymore because program 3 is already executed. After program 3, processor decides to execute program 16. Okay, so now program 3's all the registers values and stack values will be cleared. Those will be transferred back to program 3 space in the main memory along with stack values. Now stack will be freed in order to accommodate the stack values of program 16. Okay, from program 16, stack values will be transferred to the register stack from the program 16. all the values, the variables, constants, the instruction, program counter, everything will get transferred to the processor's register. This is the reason why processor also should have a dedicated stack. Since main memory has its own stack, okay, sorry, a program in the main memory will have its own stack. Whenever it is getting executed, that stack value, the values of that specific stack will get transferred to the register stack. This is the important thing that is needed to be understood when you discuss about the stack. Yeah, sure. Sir, can you explain RTL, register transfer language, at the end, and the flag register of 8086 microprocessor? Yes, this is the right question to be asked at this stage, because flag register is an integral part of the processor. So, but I'm going to explain. But flag register concept has been scheduled for the next week. Anyhow, I do have flag registers. I'm going to explain you, but not right now. After stack, I'm going to explain you people about this flag register. Okay, what is this flag register? If I start, because if I start flag register right now, it is going to take some time, which cannot be finished within the 5 minutes of the time which we do have right now. Okay, so let us finish this stack, after which I will explain you about a flag register. Is that fine? Yeah. Now, where we are? Here, right? Let us understand what is going to be stored into the stack. Okay, write it down. Why stack is required for a programmer? Why each and every program requires a stack? Stay focused. There are a few specific things that will be pushed into the stack from a program's point of view. Okay, let us take that a program. Program Anil. There is a program Anil. Okay, whenever I write a program, a few things that will be always pushed into the stack. The first one is return addresses. What is the return address? I will explain. Return addresses. The second thing is local variables. And the third one is sometimes. Flag register value. Okay, generally stack will be pushed with the return addresses and the local variables. But in some advanced computer architectures, designer will also be inclined to push the flag register value. So now let us understand. Vikram Kumar, hi, good evening. But you are too late. We are about to finish. Right from the very next week, I expect you guys to be with me right from the moment I start. Alright? Fine. Now understand what is the return addresses. When a routine calls a subroutine, routine A calls B. I don't need to explain what is A calling B. Okay, A is a calling routine, B is a called routine. When a routine calls a subroutine, this calling routine's return address will be pushed into the stack. Okay, first thing, that is what a return address. Did I make it myself clear? Function A calls function B. That means that A is a calling routine, B is a called routine. So whenever, every time, if a routine calls a subroutine, calling routine's program counter value, that is the return address. Program counter value or return address, one and the same, should be stored. Okay, program counter and the return address, whatever it is, I mean, both will be one and the same. The program counter value should be pushed into the stack. Okay, local variables. What is the local variable? Of course, what's the time right now? 1 more minute. Of course, you know what is a local variable. When you declare a local variable which is specific, which is pretty much local to a function, then these variables will also be pushed into the stack. Okay, And what's the flag register? Flag register, anyhow, I'm going to explain you in the next lecture. These three things will always be pushed into the stack. In the older computer architectures, just only these two things will get pushed into the stack. In the advanced computer architectures, stack will contain all these three things. Return addresses. Function A calls B. A's return address will be pushed into the stack. Okay. A program will have a local variable. Will have a few local variables. All those local variables will be pushed into the stack whenever those are used. And flag register value. Okay. These are the things that are always pushed into the stack. Okay, Sanket Sahasrabuddhi. Next lecture, my lectures will always be on Friday sharp 6 o'clock p.m. Every Friday at 6 o'clock, I am going to meet you people. I want you people to be present exactly at 6 o'clock to be with me, because in architecture, if you miss something, you're going to miss a lot of things. You are going to miss many connections. Okay, because everything is a linked chain. Even if you miss a single link, you're not going to understand. Already you asked many of the questions which I already covered in the previous weeks. So I expect you guys to be present sharp at 6 o'clock every Friday. So this is what all about for today. Next week I'm going to push from where I start today. Okay, so we finish with this. Flag value will be depend on the program requirement. Lokesh Parab, yeah, of course you are somewhat correct, somewhat wrong. I'm going to explain you completely in the next week about a flag register. Did I make it myself clear? That's it for today. I'm going to see you people next week, same time. Okay? Yeah. Good night.